Assalamualaikum warahmatullahi wabarakatuh. My lecture is about the heat capacity and it is from the Kittel book. I will discuss in my lecture the entropy, change in entropy, free energies and the heat capacity. Entropy, it is the measure of disorderedness of the system. It is the measure of randomness of a system. It decreases on cooling below the critical temperature. As you know, when you increase the temperature of a substance, temperature of the material, then the thermal vibration or the velocity of the molecules in the material will increase. On the opposite side, when you decrease the temperature of the material, then the thermal vibration or the velocity will decrease. It means that the randomness will be decreased, and by decreasing randomness, the entropy will decrease. It is low in the superconducting state, so the superconducting state will be the ordered state because the randomness is very small, and it is high in the normal state. It is shown on the graph. It is the graph between the entropy and the temperature. The green line shows the entropy for the superconducting state and the orange line shows the entropy for the normal state. This is the critical temperature. You can see that at the temperature the entropy for the normal state is high, and at the same temperature entropy for the superconducting state is low, and it is shown by the dashed lines. Change in entropy, it is small. You can calculate the change by taking the entropy for the normal state and entropy for the superconducting state and subtracting the entropy for the superconducting state from the normal state, and you will get a very small change. For example, in the aluminium it is of the order of 10 to the power minus 4 k beta per atom. Here k beta is the Boltzmann constant. A small entropy change means that only a small fraction of the conduction electron participate in the transition to the ordered superconducting state. The conduction electrons are in the normal state, and you can say that the conduction electron from the normal state will move towards the superconducting state, and there will be very small, their value will be very small. Free energies, low in the superconducting state and high in the normal state. It is shown by the graph. This is the graph for the free energy and the temperature, and you can see here that the orange line is for the free energy for the superconducting state and the green line is for the free energy for the normal state. And you can easily see here that the free energy for the normal state is higher than the free energy for the superconducting state. For the superconducting state, we take the magnetic field equal to 0, and for the normal state we do not take the magnetic field equal to 0. B is not equal to 0. B has some value, some specific value, and this is the transition temperature. At the value of transition temperature, both the lines merge. It means that it is a second order phase transition. Heat capacity. Normal state has the electronic, lattice and the nuclear quadrupole contribution at the T, and the electronic contribution is due to the electrons, and the lattice and the nuclear quadrupole contribution is due to the phonons. And this is the equation for the heat capacity. C is equal to gamma T plus AT cube. C is equal to heat capacity. Gamma is the Sommerfeld parameter and A is the constant which depend upon the characteristics of the material, and this is the electronic term and this is the phononic term, and you can easily see here that the electronic term is linear with the heat capacity, but the phononic term has the T cube dependence, and C by T is equal to gamma plus A T square, and this is the graph between the C by 2 and T square, and where gamma is the Sommerfeld parameter, electronic contribution is small. Here the electronic contribution is small, and the green line is for the normal state and the orange line is for the superconducting state. This is the critical temperature value, and C by T is equal to 0.59 plus 0.05 T square. 0.59 value is the for gamma Sommerfeld parameter, and 0.05 is the experimental value for the A, which depends upon the characteristics of the material. See, electronic by gamma T have the small values, so that's why we use the log scale, and it is exponentially depend upon minus 1 by T. This is the graph between the C electronic by gamma TC and the TC by T, and here the values for the C electronic by gamma TC are the 0.001, 0.01, 0.1, 1.0, and as you know that these values are very small, so that's why we use the log scale. Log scale is used when you have very small values, and this is the value of C electronic by gamma T. This is the experimentally calculated value, and exponent minus 1.39 Tc by T, and from this you can easily see that C electronic by gamma T is exponentially depend upon minus 1 by T, and suggestive for the excitation of the electrons across an energy gap, and it is suggestive for the excitation of the electrons across the energy gap. Friends, if you like my video, then please share it to your friends, and please subscribe my channel. It is very important for me, and please see the next one.